Hello everyone, I am Profir-Petru and I will be presenting Flexeme. This is joint work with my supervisor, Earl Barr, and my co-authors, Santanu and Allamanis. Flexeme is a tool to separate tangled commits into their constituent atomic patches and is built on top of a multiversion nameflow graph. But what's a tangled commit? Well, a tangled commit intertwines patches that solve unrelated concerns. Here, the developer changes how color schemes are handled, as well as how characters are rendered in a terminal emulation program. Ideally, the hunks labeled 1 and 2 respectively should be committed separately. But what's the harm in leaving the changes tangled? Why should we separate them at all? Well, atomic commits enable us to use an array of bug localization techniques on version histories, as simple as git bisect or as complex as neural approaches. For the former, this allows a cleaner verification of a fix or a breaking change. For the latter, it reduces the bias in the training data that could otherwise mislead the approach. Atomic commits also allow a cleaner interlinking between requirements and the history of their implementation, enabling semantic history slicing approaches, and also facilitating code navigation or comprehension. To facilitate this, Flexeme starts from the version history of a project to build multi-version representations of code. First, by constructing PDGs for contiguous versions, then annotating them with nameflows. To discover atomic commits, we start by assuming each change is a separate concern represented by the change's k-hop neighborhood. We cluster them back using agglomerative clustering by considering the graph similarities of neighborhoods. Developers are then offered candidate atomic patches. For our 𝛿-NFG, we start from Leon-Patterson's innovative multiversion interprocedural control flow graph. We augment it with data flows, similarly annotated with versions, to get our notion of a delta PDG. We add a subset of data flows as nameflows, which in addition to a version labeling, are also labeled by the names that flow along them. It is in this structure that we explode the view into k-hop neighborhoods and then recluster using Weisfeiler-Lehman graph kernel for similarity. A graph kernel enables a notion of similarity over graph data. Pragmatically, we can cluster our graph data into a vector space where the dot product captures precisely our kernel's notion of similarity. Under these tools, the Weisfeiler-Lehman graph kernel is a meta-kernel derived from the graph isomorphism test under the same name. The core idea is to compute the kernel of graphs, where the labels get message passed and aggregated at each iteration. Given this framework, we use the rooted subtree graph kernel. Intuitively, this counts the number of downstream code behaviors, or subtrees in our 𝛿-NFGs, that match across our k-hop neighborhoods. To ground our results, we consider two baselines: Barr et al.'s elegant use of DU chains and Pârțachi et al.'s work which, although focused on studying the bias introduced by tangling, produced a strong commit untangler using confidence voters. Both methods need data supplied by static analysis. Our 𝛿-PDG provides almost all the information we need. We pre-compute version history data to provide the rest. To reproduce Barr et al., we first take a data flow-only view of our 𝛿-PDG. We separate the flows by kill statements, such as assignments, to obtain DU chains. Due to the construction of our 𝛿-PDG, these chains are already intersected with the considered patch. Barr et al. Then formulates two relationships across which concerns should be the same, when the changes are of uses of the same definition, and when the definitions change in tandem with one of the uses. We propagate the relationship across our chains by message passing, starting from the hypothesis that each change is a separate atomic concern. To reproduce Pârțachi et al., we pre-compute a file co-occurrence matrix from the version history and derive a call graph and a data flow graph from our 𝛿-PDG. Pârțachi et al.'s approach works over diff hunks, so we maintain a mapping between the hunks and their nodes in our structures. We compute their confidence voters as described in their paper, adapting package distance to namespace distance, which, due to how these are written in C#, maps cleanly. We use maximum linkage agglomerative clustering, starting from the hypothesis that each diff hunk is an atomic task. The original algorithm assumes an oracle for the number of concerns, that is, the resulting clusters, and since we have a data by construction, we provide it to our reproduction. To validate our approach against the reproduced baselines, we consider two performance dimensions: accuracy and runtime. For runtime, we consider only the cost of performing the untangling task. One reason is the use of our 𝛿-PDGs to derive the structures for the reproductions. Another is that we see this cost as hidden from developers or amortized, either in compilation or in build time. For accuracy, we consider it at the per node level as presented here on the slide. Due to the randomness in initialization of cluster labels, an algorithm may compute a permutation of a ground truth. It is unfair to penalize tools in such circumstances, so we employ the Hungarian algorithm to find an accuracy maximizing permutation before reporting accuracy. This is applied to all tools. To generate a corpus on which we know the ground truth, we borrow the methodology from Pârțachi et al. We first find candidate commits that we consider reasonable to tangle, contiguous commits under a per-developer projection that are within 14 days of each other, commits that touch files within the same namespace or with a high prefix match, those that touch files that are often co-committed. In all cases, the commits must not have multiple keywords that indicate a concern, such as multiple uses of fix, bug, feature, implement. Once we have our candidate commits, we attempt to git cherry-pick each commit in a chain onto the parent or the first commit in the chain. Not all such cherry-picks are successful, and even in the successful cases, we perform a post-processing run where we assess the number of surviving changes from each commit in the chain. Here, in Table 1, we can see the statistics of the projects we employed this Corpus Generation technique on. In Table 2, we can see the generated tangled commits. We did generate 4 concerned commits as well, however, they were too few to make statistical conclusions on. These tangled commits, while artificial, capture the intuition of a developer forgetting to commit their workspace before starting new tasks. The state of the art before Flexeme was on opposite ends, fast but inaccurate, or slow and accurate. While Barr et al.'s is almost real-time, despite their low accuracy on our data, Barr et al. Validated their approach in a user study, finding developers considered their suggestion accurate and complete for the tasks that they were asked to judge. In Pârțachi's case, we suspect data dependency reachability queries to take up most of the time and to scale badly to larger patches. Comparing each tool to 𝛿, our implementation of Flexeme's methodology, we can see an improvement in accuracy over the DU chains approach and over a confidence voters approach, and at a smaller cost in runtime. In our case, the degenerate cases are typically those that end up producing large collections of graphs that we should then recluster back. We also consider porting over Pârțachi et al.'s approach fully to our 𝛿-PDG and dropping the change coupling confidence voter, only that one, since it is not available from our structures directly. We obtain an algorithm which slightly outperforms 𝛿, but which scales worse to large graphs. Overall, we propose 2 approaches based on our 𝛿-PDG and 𝛿-NFG that improve the state-of-the-art in untangling commits in terms of accuracy at a small runtime cost compared to a much simpler and thus efficient approach due to Barr et al. In this work, we make use of agglomerative clustering to get our final recommendations. We leave exploring other approaches to clustering or reclustering changes in our setting of untangling commits as future work. Further, for our multiversion representation of code, the 𝛿-PDG and the 𝛿-NFG, we show only one use case, that of commit untangling, which is not immediately associated with PDGs. Future work can focus on expanding ideas due to Lee and Patterson explore the use of eStructure for static analysis work on multiple version, such as for patch validation for backporting. In this talk, I first introduced the problem of tangled commits. I then presented 2 new multiversion representations of code. First, the 𝛿-PDG, which follows from Lee and Patterson's multiversion ICOG, and then the 𝛿-NFG, which further includes variable name propagation information. Finally, we show how a graph kernel approach and a confidence voter approach over our 𝛿-NFG and 𝛿-PDG respectively improve the state-of-the-art in commit untangling at a small runtime cost. Flexeme is available at the site on this slide, and you can scan the QR code for a quicker access. Thank you for your time.